So we had talked about a specific example of a binomial distribution, and it's good for us to get some intuition about the situation, but what we want to do is to be able to generalize this. Now, from the last example, we had the following outcomes. So if the probability when x was 0, we found that there was one way of getting 0 successes. So we had 0.2 to the power of 3. The probability of x being 1 was 3 ways at 0.2 to the power of 2, 0.8 to the power of 1. Probability when x is 2 is very similar. And finally, the probability where x is 3 was similar still. And I'm going to write this with a little gap here. Now, what I want you to see first and foremost is that there is a pattern. The power of the failures changes by 1. In this case, as I go from x is 0, means I have 3 failures. This decreases by 1 as I go through my list that way. And in fact, you could and should interpret this last one as having 0.2 to the power of 0. So anything to the power of 0 is 1. Now, at the same time, the successes have a similar pattern going the other way. And in fact, you could and you should interpret this line as having 0.8 to the power of 0. And anything to the power of 0 is 1. So that means in general, you would expect that the probability where x is equal to some value k, this means that you've got k successes. And the idea there would be, look, if you have k successes, the probability of success was given by little p, and you should have k of them. The probability of failure is given by 1 minus p because it's a 2-outcome trial. And you have n minus k of those. Remember, at each stage, if you want to get in and out of your tree diagram, you have to go through n stages. If you take the exponents in each stage, they have to add up to the total n equals 3. And if you look at what we've done here to generalize, these do in fact add up to n. So going through each individual branch is pretty straightforward. You just have to figure out how many successes are in your branch, multiply the little p by that value, and then the 1 minus p by the opposite value. What is a little bit more work is the number of ways you can do something. Okay. Now, here we are interested in the number of ways to choose, let's say, 1 success out of 3. So if I go down here, the number of ways to get 1 success of 3 objects or 3 trials. We don't care about the order. So I'm hoping you see that this becomes a combination problem. This says if I have 3 objects, I'm interested in the number of ways I'm choosing groups of 1. So by definition, this would be just the combination formula. And if you were to sit there and calculate this, you'd have 3 factorial over 2 factorial and 1 factorial, which would just end up giving you a 3. And that's exactly the number in the front. And if you went through and you did the same thing for each of these, this would be, for instance, the number of ways to choose 0 objects out of 3, or the number of ways to choose 3 objects out of 3. Each of those only has one way of doing it. So I'm hoping that you can believe that the number of ways gets generalized, and we put k and a combination upstairs. And this is a formula for the probability of each outcome. And so this is the formula essentially for the PMF. I could just dump out the formula for you, but I think it's really important for you to be able to understand where those terms come from. Now, this formula depends on the value of n and the value of p, right? Certainly you can see that each of those things appears in the formula. So what we do is we say that if a random variable is in a binomial setting, we use this notation. We'll put an x and we'll put this squiggle BNP. And we'll say that x is binomially distributed. That's what this notation is going to stand for. The parameters here are n and p, where n is always understood to mean the number of trials and p is always understood to be the probability of success. Now, in the example that I did, remember when we have a probability mass function, we can always draw a bar chart for it. And if we draw our bar chart, in our example, we had these particular values. We had a 0, a 1, 2, and a 3, 0.008, 0.096, 0.384, and 0.512. So we can break this up into the categories 0, 1, 2, and 3. Here's our bar chart. It is very, very little in this first bar. The next one is almost up to there. The next one gets close to 0.4. And then the next one is slightly above here. In this example, we've got a binomial distribution where n is 3 and the probability of success is 0.8. And so every binomial distribution is different because you can have infinitely many different values for n and p. You can have infinitely many different values for our different graphs here. Now you can note that there's some things that you can predict. If p is very, very large, if it's close to 1, that means you're going to have many successes. The chance of having successes is far greater than failures. And so your graph is going to look something like this. Since this is a mass function, we're now going to introduce a term that's relative to where most of the mass is. So most of the mass lives in these two bars. But you see that there's a little bit hanging over to the left. So it's almost as if somebody took their left hand and grabbed where most of the mass is and pulled it to the left. So this has been called, this is a graph that's skewed left. So when your probability of success is close to 1, you would expect a left skewed graph. If your probability of success is close to 0, then you would expect the opposite in a binomial distribution. Most of the mass in your mass function is here, and it's as if somebody had grabbed with their right hand and pulled to the right. So we would say that this graph is skewed right. So if you have a probability mass function that's binomial and p is very close to 0, you would get graphs that are right skewed. Now, is this really a mass function? To really be a mass function, the sum of all those probabilities better add up to 1. And so when we are talking about this binomial probability mass function, it turns out we have an expression kind of like this. And some of you may have seen this before, and some of you may not have, and that's fine. But this is technically something called the binomial theorem. And what this does is it allows you to say, okay, take this value and add it to this value, and the whole thing gets raised to the power of n. This is 1 to the power of n, which is 1. So yes, you may not know the binomial theorem. You can look it up on Google. But essentially, this is what guarantees that we do have a mass function. The two things that we are most interested in figuring out are the expected value and the variance. Which outcome do I expect to see most often? Now, I'm going to post these notes online here, but it's long and it's technical and it's mathematical. It turns out that the expectation, just using properties of summation, gives you a handy little formula for the expected value. It's just n times p. And that makes a lot of sense. If you have a chance of success, probability of success, point whatever, all you have to do is multiply it by the number of trials, and that would work out. The variance ends up being equally similar. It's just n times p. I write q down, but technically we should be writing n times p times 1 minus p. So in our example, where we have a binomial variable with 3 and 0.8, the expected value is 3 times 0.8, which is 2.4. The variance would be 3 times 0.8 times 0.2. So they all turn out to be very straightforward numbers, very straightforward to calculate. And if you wanted, you could take the square root to get the standard deviation. So this tells us everything that we need to know about a binomial distribution. There are ways that we can use technology to calculate things like the expectation, the variance. You can use technology to find the probability mass function, the cumulative distribution function, and to draw a graph.